Mexico State University, and we performed a first order class 1 level loop. I'm Garrett Smelker. I was the captain of the team and the president of our chapter. I'm a senior in surveying engineering and civil technology. This is Adalberto Guerrero. He is a senior in surveying. This is Laura Hardin. She's a sophomore in surveying. Felice Hardin, or Felice Mora. She's a sophomore in surveying and civil engineering. And Julian Heckman down on the end is majoring in industrial engineering and surveying engineering.
Yep. A bit about myself. Been surveying for 20 years and had the opportunity to go back and go to school and work with the students here. Kind of felt a little bit out of place, being 4 years old, and here I am with a bunch of young students. And it's pretty impressive watching how everybody works together. And when we picked out this project, doing this high precision level, and back in my mind, I was just thinking it's just a level loop. You know, what's so hard about running a level loop? But after going through the project and working with the students, I saw that it was a lot more than just running a level loop. Just simple things as reading and understanding the standards and specifications and applying them. That was pretty much a learning experience for me, and at the same time, not only for me, but being able to help out the students that are lower classmen. That was pretty fun too, to watch them doing little things as setting up the tripod and setting up the level, getting the field notes ready. That was all pretty fun for me to watch and help them out with. But talking about the scope of the project, like I mentioned, we wanted to explore the high precision vertical control. At the same time, we already have a control system or a network set up out there, but we wanted to extend it to the east side of the campus. And at the same time, we use GPS observations on these control points to find the geoid height. And right there, it allowed us to gain deeper understanding of vertical control applications and experience a specialty within the surveying. And like I mentioned, the high precision vertical control, it takes us to this height modernization to understand it a little bit better. I'm just gonna go over the slide. I'm pretty sure you guys seen that illustration before. But this height modernization, it establishes accurate and reliable heights using GPS technology along with the traditional leveling that we're used to, gravity and remote sensing methods. Also tie the control coordinates to long-standing vertical control, which is what we did, extending the network that we already had on our campus. Also, it improved the geoid to get a better ground elevation projected from the ellipsoid. Talking a little bit about the control that we use, NMSU, we already have a vertical control network. Some students started this project back in 2010, and they brought the first order control to NMSU with the epicenter beam in the middle of the campus at Riley. You can see that on a poster, or you'll see it on the slides later on in the presentation. There was 3 previous loops that we tied into Riley, A245 and H245. And our goal, it was, like I mentioned before, to extend this vertical control or the network to the east of the campus. Also, we got some elevations along some other benchmarks that were along the way, and we got redundancy on a couple other benchmarks that we have. And these are the control points right there. This first one right here, these are the first 3 points that we use, the A245, H245, and Riley. This is the center of the campus, which is right there. And our bench loop, we ran it from here, we went west, south, and east towards the campus. And then of course we have to run it back to check into Riley. Those are our control maps. I'm gonna pass it on to the next student.
We decided to do our first thought was we do a first order class level loop. And then we also decided we would take GPS observations on both Riley and Kiss, the beginning point and the top point up by the Pan Am Center at essentially the middle of our loop. The field notes were processed by Garrett, and we went through the computations with an Excel spreadsheet. We analyzed them, we compared them to the standards for a first order level loop, and then we got the project ready. In New Mexico, there are many problems with surveying outside for a long time. And the general needs for any surveying crew, you need reflective materials, so if you get in traffic, which we had to, you are visibly seen, first aid, so if anyone is injured, you can take care of that. And personal safety, it can get very hot in Mexico, and that we'll speak more about that. Traffic, fortunately we did our project during the off-season between semesters, so there was not as much traffic as there could have been, but because at NMSU they still had students on campus and they still were having local events there, we had to keep an eye out for the traffic. The temperature variations, you start out in the morning wearing a sweater and you leave in the afternoon wearing a t-shirt. Fortunately, it was in early January when we did this, so it didn't get to the extreme levels of heat that it can in the summer, which can be upwards of 100 degrees. Staying hydrated even in that time of the year is necessary because we do live in a very, very dry climate, and getting dehydrated is a very high possibility. Locally, we have a standard of if there's lightning within about 10-mile radius of an event, sporting event, anything, you need to shut down and wait for about 30 minutes for hopefully the lightning to move away. We didn't have any lightning or any storms that day, but if we had seen lightning, because we are using infrared rods, it would have been very prudent to quit that day. And I'll give this slide, please.
Okay, so the equipment that we used a Leica geodetic level with high precision. We also used 2-meter infrared rods that were calibrated by NGS when we purchased them in 2010. These rods have been used not too often, so they were precise. We used 2 ball bearings when on concrete. We also used 2 turtles when on soft surfaces such as grass and dirt. We used a fixed wooden leg so that way we had no slip and no flexing. We used a thermometer and barometer, which we took measurements when set up at each point. We also used Trimble stations for our GPS. We used Adjust for our least squares adjustment, and AutoCAD, which we use for our poster and to make everything else look nice and presentable. So the regulations for our first order class 1 loop is for the difference in foresight and backsight would never exceed 2 meters. The maximum sight length due to earth curvature, which is 50 meters, so we did not exceed that. The minimum ground clearance is 1/2 meter. The maximum loop closure is displayed with this equation. So our first loop from Riley to Kiss ran, like Bertha was saying, ran from Riley to Hyatt, down to EFB, to Pseudo, to STSW, and then up to Kiss. That was 1.4 miles in length, and we added 3 new control points. The last level loop ran from KISS, back to STSW, to Pseudo, and back to Riley. And that was 1 mile in length.
So for our measurements, we had 82 points, 82 turning points, which is a lot. We had 5 control points. We did backside, foresight, backside, so that we would only have to do the loop once. We don't want to do it twice because it took 16 hours to do both loops. We recorded the distance each reading. We did this because we have a data collector. Our data collector failed, so it was good that we had a backup plan to make sure that we had all our distances recorded. We used the temperature and barometric pressure recorded on each setup. We didn't really have to do that because we had the Invar rods, but I mean, that's still one of the requirements for a first order. So then we did the reduction of our field notes. So we ended up with a misclosure of 4 millimeters, and that falls under our maximum allowable misclosure by a factor of like 0.5. Our maximum sight distance on all our data points was 46.2, so we never hit the 50. Our average sight distance was 21.7, which is extremely short, so it did take a long time. And it took a long time because we had essentially a lot of vertical relief. We were going uphill the whole time. So this is our Excel file. We took our field notes, we put it into Excel. We compared to check for blunders to make sure that we didn't accidentally type something wrong. And as you can see, it kind of does all the calculations for us.
So this was a pretty cool part because the underclassmen have never seen or heard of a least squares adjustment. So myself and Berto took it on us to kind of show them what we're doing. We went ahead and used the Adjust program that's free for educational purposes. We held the H245 and A245 from the previous loops that students had ran. They're located on the railroad, and it's about the closest first order control in the area. A245 is 3 miles from campus, and H245 is about 1.5 miles. These loops, this is a non-weighted solution. It's minimally constrained. We went ahead and did non-weighted because we used the same procedures as the previous loops had done. We used the same equipment, and since we balanced our foresight and backside, we really didn't see a reason to weight it. We built it. When you build it, it's kind of, if anyone's used Adjust, it's a great program, but it's kind of tough to use. And so we had to go through, and in our calculations, you can't just input foresight, backside. You got to get the height difference between each shot. But Adjust also allows you, if you have a large standard deviation, you got to blunder somewhere. We had a couple pop out. We went back. Since our data collector was not working correctly, it ended up just being input into Excel. We put the wrong numbers. We were able to tighten it all up. Ended up with 9 degrees of freedom, a standard deviation of about 2 millimeters on each point. Then our static, we went back and did static observations on all of the points. Now the NGS, in order to have a solid first order static observation, you would have to do it 3 sessions, 4 hours each over a 2-day period. We just didn't have the time and the resources to do that. So what we went ahead and we did was we did a 2-hour static observation on the start of our loop and at KISS, which is where we turned around and came back. We processed it through Opus, and Riley has a first order ellipsoid height already established. So it was kind of neat to see that with just a 2-hour, we hit within 4 millimeters of the published elevation. Kind of gives you a little comfort when you're using Opus in the field, running RTK. You just want to get a relative elevation while you're there. It's pretty close. It allowed us to find the geoid height, which was the orthometric height that we leveled, minus the ellipsoid height. And you'll see that over the distance of just over a mile between Riley and Kiss, it's about a 2 centimeter difference in the geoid, which our elevation on Riley and the elevation on Kiss, there's a difference of about 2/10 when it's projected up to the orthometric height in your GPS. So it just kind of shows the impurities with the geoid. You can see that you can trust it over a short span, but in 2/10 and less than a mile, it's more of a relative if you go ahead and use Opus. So with our final results, these are all the adjusted elevations that we came up with. It looks like I lost the battery. Our standard deviations are 2 millimeters on almost all of our points and about 3 millimeters at KISS, but that's at 1 sigma, so to have that 95% confidence interval, we would do it at 2 sigma, so it'd be 4 millimeters, 4 to 6 millimeters on each one. That's pretty good for the distance of our loop over the years, the span that we've done this. Our ellipsoid heights came out, like I said, we had a 4 millimeter difference. And when you look at our geoid heights, you can see the 2 millimeters in just less than a mile. It just shows that the model's not perfect. With high modernization, reporting all this information, we can improve the geoid and make it easier so we don't have to keep running first order levels. Some of the challenges with this project, one of the requirements is to have a collimation, a C-factor test performed at before and after each day. And you need to fit within 5 seconds on your results. And we couldn't get it below 5.5 seconds. And I spent hours adjusting that sucker. Being university equipment, someone's used it and stripped one of the nuts on the bubble. And so we did not have the time to send it in to be serviced. So I was able to get it down to 5.5 seconds. That was about the best we could hope for. I did do it every time we set up and tore down. Electronic data collection, getting university equipment, someone changed some settings. We got out there and didn't realize it. File became corrupted. But because we took field notes in the field book, we had the backup, we didn't have to restart. The biggest thing was the field crew experience. I've been doing this for about 5 years surveying. Bertha's done it for 20, and the rest of us are real low on experience, real low on the education. But we didn't see that as it was going to hurt us. Saw it as a learning opportunity. This is something I've never done. I thought it was just a level loop myself. Turned out to be a lot more. Going through the specs, going through the adjustment. It was a good learning curve for everybody, and we tried to bring in the younger students and encourage them. At first, they kind of didn't want to do this. I think overall that was the whole point of this project, was to teach everybody a little bit. So some of the things we learned about it is this really a first order class 1 control? If you're going to go check by check on the list, no. We didn't meet all the specifications. There's pages of them. Some of them we just could not meet, such as the C-factor test. We chose the ones that we felt were really important to us, and we worked really hard to meet those. So even though it's not necessarily first order class 1 on the checklist, you can trust these points with a 95% confidence at 4 millimeters at our farthest points. The other thing that we learned is there's a reason NGS is no longer going to supply us and maintain our vertical control network. And it's because it requires the large crews. It was time consuming. We spent 16 hours in the field running a 2-mile loop. And the equipment is so expensive. The rods are $9,000 a piece. The level's $5,000. The rod can't be scratched on the bottom. They have to be certified. It just turns into a large hassle. And it's not necessary anymore if we can maintain and build on high modernization like the NGS objective is. Hopefully we can improve the geoid model, include remote sensing, and these steps are no longer necessary. They can be performed by a specialty, and it's just not economical anymore. That's all we have. We're open for questions. Thank you. Yes, sir.
What words would you describe your feelings when the data collector was corrupt?
You know, it wasn't as frustrating as you think, because it happens more often than you think at a university. So once we made sure all the rest of the settings, our measurements were coming out correct, we were going to do it with the field book anyway.
The hardest thing is when we inputted the data, it took us 2.5 hours, and we had to double check, make sure we can.
Yeah, the keying in it, so that's where I made my blunders. We had the delta column going, and when I saw something, I saw 2 centimeters, well, I know that's not right. We were measuring down to millimeters, and it was just keying in those numbers.
Questions from the judges?
One more question. Can you believe that those in-bar rods cost more than that level?
Is that surprising? And the thing about them is we were, according to the specifications, you're supposed to have 3-meter rods. The 3-meter rods have a couple problems. They're too tall to fit in the back of your truck, and they cost a lot more than the 2-meter rods. And you can't store them. At the university, we have a small storage room. That's why they went ahead and bought the 2-meter. Saved a couple bucks in the process.
Even the way you're supposed to handle them, I mean, you have to be real careful with them and trying to, don't let the bottom touch the ground, and why? Just don't do it. So we have to teach them stuff like that. It's important for all of us and all of us.
How are you going to protect those rods when it sounds like they're pretty rough on the equipment?
Yeah, it's tough. The seniors are about the only class that ever really get to touch these rods. The problem is more of the underclassmen in experience. No, not these specifics, right?
Just threw you under the bus.
But these rods have been taken very well care of, and we use the ball bearings and the turtles. It's 2 reasons. It kept it off the ground from getting scratched, and it also gave us a high point to set the rod on every time. So we put that ball bearing on the cap on the way up and back. So we had a single high point. Some of the caps are warped a little bit. Just help save the rods.
Any questions from the audience?
Can you give me an example of the first order spec that you didn't meet? I know there's pages, just one.
So collimation is probably the biggest one that we were really worried about, because it just, you're not perfectly level when you turn 180 and shoot your foresight. We were really kind of worried about that. We tested it a few times on the peg test. It worked out, but I think our results could have been a little bit better if we would have been able to send it in for servicing. There's a couple others. I noticed after we did it that you're supposed to have a maximum distance between your foresight and your backside heights, and there was a couple times we exceeded it. I'm not too worried about it because we did balance our foresight and backside, but that was one that we probably should have caught before. We didn't catch it. It happens. That's the biggest thing about these specs is there's so many and they're so broad that you almost have to have somebody either studying them or an expert in them, because you start doing one and you forget about the other.
Does it first order require the instrument to be shaded at all times?
I don't believe so.
Okay.
It may. I may have.
I
I don't believe so.
One more question? Just one more. Okay.
Thank you, sir.
Thank you very much.